All right, good morning, students. Sorry it took me a minute to get the software loaded, and I'm making sure that OneNote is doing what it's supposed to do. Hope everybody's doing okay today. Hope you're, I don't know, staying safe, staying healthy. If you're here, I wish you'd comment or say something to let me know that you're here and that you can hear me okay. That would be very helpful. While I wait for OneNote to do its thing. Nobody? Nobody's here? It says there are 5 of you on here. There's a slight delay that you guys should be aware of. It's a delay of about 25 seconds. Hey, good morning, Kira. There we go. That's all I wanted. I'm just curious to see who I'm talking to. I've basically forgotten all of your faces at this point. So just know that. All right. Good morning. Oh, y'all had to make a channel? I'm sorry. Morning, Lauren. Good morning, Emily. Glad y'all could be here. Just so everybody understands, I'm just waiting for my internet to load something because the way that I've been doing it, I'll show you in a second, is when everything works, and I only started having issues yesterday, but when everything works, I can actually write on my tablet and it sends it to the screen so you guys can see it. What I was previously using was a whiteboard, and that was terrible, and it didn't work very well. But anyway, glad to see you guys on here. I hope your other classes are going okay. I hope you're excited for our exam, which is soon from what I remember. I guess in my email it said something like the 7th. But now I can't remember. All the dates are kind of merging together at this point. Let's see here. Seriously? Still not loading the thing that I told you to load? Let's see. What did I say? Here we go. No, it says it May 14th. Where did I see it? This said the 7th. I remember looking at it. You were there.
When you were on AV.
Well, why did they say the 14th here? Whatever. Anyway, the exam will be here before we know it, guys. So just be prepared for that. We are on the last unit. This is the last thing that they could possibly ask you questions about, which is why we're taking it seriously. At least I hope you're taking it seriously. And you're doing the notes like I've asked you to. But this morning, the plan is when my computer decides to finally load and do its job, is we are going to look at those 7A problems. And again, the reason that I'm having a delay is it just hasn't done anything yet. So it'll be here in a second. Yeah, it used to be, okay, so it used to be the 7th. Well, they need to update their website. But yeah, 14th is our target. So it's here in less than a month, and then you guys will be done with at least that. I hope your other classes are going well, though. I'm really curious to know what those classes are like. And I will admit, I trust you guys to be a little more mature than some other students. That's why I'm kind of giving you free reign and kind of guiding you and saying, look, this is what you need to be learning about. But honestly, my other chemistry classes are keeping me pretty busy. They're a little needier, which is fine. That's my job. They do take up a little bit more time. All right, I'm going to restart OneNote because it's not doing what it's supposed to. Go figure. Go figure. Please do what you're supposed to do, you stupid thing. Uh-oh, where our class is going awful. Um, well, Kira, I'll be honest, I don't think we're going back to school. Um, but if we do go back to school, don't worry. I will think of something for us to do, and it'll probably include cleaning all that glassware that I'm so excited about. After exams in our class, not a whole lot. I'm actually probably going to talk to administrators and just straight up ask them and say, look, if we're done with the AP exam, what more should I be doing with my students? And if they say something like, oh, you still need to provide enrichment, you still need to make sure they're doing something, well, we will do something, but it won't be very high stress. I don't know. Here we go. Here's my compass on this. What has the great Doug Jones said that he's going to do after exams? What's he said he's going to do after his AP exam? Hmm. Well, we got an article that Miss Robinson told us to read that was about South Korean schools and how they said one of the things you cannot do as a teacher is assume that you're in regular school anymore. Um, and so one of the things that I've tried to do with at least my classes is I don't structure it like a normal class. I try and say, look, here's what I deem to be a reasonable amount of work, and then I usually cut that in half. And then I try and make it a little fair. I try and make it so there's not so much work. But I have heard that from some of my students in my other classes, is they just say that they have more work than they ever did in regular school, which I think is ridiculous. But whatever. Hmm. I would think that Doug Jones would already have explained that to you all. All right, why are you not working? All you gotta do is load one page. Well, that will be nice. Good morning, Ashley. We're going to talk about some really advanced equilibrium stuff in a second. But you're welcome to join us. But it's going to get very confusing here in a second when we start talking about KC and KP. I don't know. I'm honestly kind of disappointed that an entire year of AP chemistry work is going down into a 45-minute two-question test. But that's just me. That's just me. Well, I would love to know why this isn't working. Oh, that's why it's not working. Hold on. Move that in there. Cut. What? That's not part of an assignment. Delete it. There we go. Wait, is that why it wasn't working? Now I'm really confused. Page. Undo. 7A. Copy. Paste. Okay. Maybe now it'll do what it's supposed to do. Maybe. Probably not. Close. Yay, it's working. All right, great. Let's get on with it. So here we go. We are looking at those Unit 7 problems that you guys are so concerned with, and we'll just see how it goes. Are you talking to me, Lauren? Life is real close to a living hell right now because building a house during coronavirus is not fun. But it's okay. It's going to be over eventually. All right, let's take a look at these 7A problems. I'm just kidding. I mean, obviously it's terrible, and they're digging a well right now, and I'd love to be there, and I'm stressed about it. But I'm very thankful to have a job, and that actually is not a joke. I'm very thankful to have a job. There we go. Number one, the following reactions, and then we're going to write expressions for the equilibrium constant Kc. So, balancing, we're not going to waste any time with. If you guys don't know how to balance by this point, you're going to have a rough time on your exam probably. So we'll just fill this in real quick, and hopefully it'll load. Hopefully it'll load. Please do it. Please do what you're supposed to do. Am I in the right place? Yeah, I'm in the right place. Should be loading right now. So annoying. But anyway, I have a 3, a 4, and a 4 written on my tablet, and it's not going on here yet. The only thing I can imagine is it's loading all the pictures of y'all's notes, and that's what's hogging the bandwidth right now. But, you know, hopefully it'll load here in a second, because this is ridiculous. Yay, there they are. 3, 4, and a 4. And so now that we have all that stuff, writing KC expressions I don't think is really difficult for any of you guys. I think that you pretty much get it. You know that gases we are going to write, aqueous we are going to write in the KC expression, because those are actually participants. They're not spectators. They are actively participating in the reaction, and that's why we need to include them when we're talking about equilibrium. So we'll have H2, which is a gas. It'll load here in a second, hopefully. And then we're also going to have underneath H2O, because it's also a gas. So we have H2, which is a gas. We have H2O, which is a gas, both of which are going to be in our Kc expression. I'm not going to include solid iron. I'm not going to include that iron oxide over on the product side, because they're solids, and so we don't care. The other thing that we've got to remember is to take the coefficients, and guys, it will load in a second. I have already told it to load several times, and it's not. Daggone it. But anyway, these coefficients are going to end up becoming exponents. So H2 has a 4 in front of it right now, so that's going to end up being an exponent of 4. H2O has a coefficient of 4. It's going to end up being an exponent of 4 as well. Remember, it's products over reactants, okay? Say that in your sleep. It is products over reactants. And so that's where that comes from. All right, next, looking at B. We have N2O5 gas, and guys, I promise I've written it. It's just not showing because it's still sinking. You guys can probably see that. Yep, you should be able to see that. So I don't know. It's loading all of your pictures and everything. It should be there, but it's not. Can I stop sinking? No, I can't. You can just tell it to do it again and hope that yay, loads. All right. So anyway, that's what I got for number 1A. Now we're looking at 1B, and hopefully this one will load with no problems. Again, I'm just going to go ahead and balance it real quick because we don't need to waste our time with it. So I put a 2 in front of N2O5. I'm going to put a 4, in front of NO2, gas. And all of these are gases, so all of this needs to be included in our Kc expression. So I'll go ahead and write that out. Kc equals, please load. I'm not going to do this every day. No, don't sync all notebooks. Dang it. Be right back. Close. Reopen. I did not start having issues with this until yesterday. And then all of a sudden yesterday, it started doing this, where it wouldn't load things, and it was just a pain. All right, so there we go. We want to have all of that stuff in our Kc expression. Remember, it's products over reactants, so I'll end up putting NO2 up on top. I'm also going to put O2 up on top. And on the bottom, I'm going to have N2O5, which again, don't forget, when you're putting these things into your Kc expression, you've got to use those coefficients as exponents. So we'll end up having a 4 for NO2. We'll end up having a 2 for N2O5, and it should really be there by now, and this is really frustrating. Because now it says it's not syncing anything. It's syncing the other 2 notebooks that don't matter right now. Okay, there we go. So anyway, that's what we get. That is what we get. All right. All right, so far so good. And then we get to C. And I know this is probably not what you guys had questions about, but it's still good practice for you. So I'm going to put a 4, a 5, a 4, and a 6. All right, so that's what we get. Now all of these are gases. So all of this we still have to have in our Kc expression. So when I'm writing that, once again, products over reactants. So I'm going to put NO to the 4th. And I'm also going to put H2O to the 6th up in the numerator. And then in the denominator, I'm going to have ammonia and H3 gas to the 4th. And I'm going to have O2 to the 5th. So there you have it. Still syncing those other notebooks? Nope, we're just syncing this one. So just do it and show me. There we go. Good gracious. All right. So anyway, this is what we get. Still hasn't loaded. Well, I'm telling it to. So anyway, that's what we get eventually. I have an 02 and a 5 written there, but it's not loading. Anyway, hopefully it'll load in a moment. Let's go ahead and look at the next part. Okay, let's go ahead and look at the next one. Number 2. Kc for the hypothetical reaction given below is 256 at 500 Kelvin. And then we have this little reaction here, and it shows us what it is. But then what we're going to do is we're going to calculate Kc for these other reactions that they've given us. This is really similar to Hess's law. I know you guys remember doing that back when we were doing thermodynamics type stuff. But back when we were doing thermodynamics type stuff, if you had something and you flipped it, well, you're probably going to end up flipping your Kc value as well. So you can do this algebraically if you choose. You can reason your way through it. I don't know. I might do a little bit of both. So I don't know. It might be helpful to go ahead and start by writing what Kc actually is for this first formula that they give you. So for this first chemical equation that they give you, start writing a Kc for that. And so this is going to be Kc equals products A2B squared over reactants, which is A2 squared times B2. Hopefully it'll load in a moment. Okay, so we have that. What's going on over here? Being dumb. That's what's going on. All right. But anyway, I've written it out. We now know what Kc is, and then we're going to look and see how they've manipulated it for the other parts of the problem. There we go. So now looking at part A. Okay, let's see what they've changed. So all they've changed here is they have flipped it around. So instead of your products being where they normally are, now they've just flipped it the other way. And so when they do that, really what we end up getting is that if they flipped it, that just means that your new Kc is going to be inverted. Okay, it's going to be the inverse of your previous Kc. So I could show that to you algebraically, but basically, do we have any concentrations? No, but we don't need them. So if you invert 256, then I end up getting 3.91 times 10 to the negative 3. Wow, this is really not going well. I promise you guys, if you had seen how I've done these in the past, you would see that these usually go much more smoothly. And as I write it, it instantly shows it up there. But I don't know if it's because of the internet or what. My router looks fine. You guys can obviously see me because I'm streaming. But I have not had an issue like this before, so this is kind of frustrating for me. So you flip it. Yep, I already said that. So you invert Kc. And anyway, I ended up getting 3.91 times 10 to the negative third. Let's look at B. All right, so B does require just a little bit of math. It helps to go ahead and write down and say, okay, well, let's think of this as being Kc, I don't know, Kc prime is maybe what you could call it. So when we're looking at part B, Kc prime is now going to be for this new equation that they've given us. So Kc prime is going to be equal to still products over reactants. So I'm going to do A2B, which is my only product. It does not have a coefficient, and so therefore I'm not going to put an exponent on it. And this is all going to be over A2 times B2 to the 1/2. Now, if this would load, I could show you, but it's not loading. So we'll just take a break real quick. Excuse me. I'm just trying to let it catch up and do its thing. I don't know why it's going so slowly. No, I'm not saying it's you. I think it's OneNote. says it's loading. It is surely not. Oh, thanks. I just got an email letting me know I'm live on YouTube. Good to know. Alright, be right back. I'm going to close that again and reopen it. I'm trying to be patient. Guys, why are you not commenting on all of Mr. Burleson's announcements? That would just make his day if you would comment back to him. He won't read it, but he might read it eventually, and that would just surely make his day. I hope he's on here. I keep hoping one of these days Mr. Burleson is going to show up and watch one of my YouTube streams, and I will be so happy. And what does the X mean? Is it this stupid cloud thing? Come on, you can do it. Well, anyway, it's loading, but I shouldn't have to tell it every single time. Let's look at let's finish this one up. So as you can see, it's been manipulated just a little bit, so we have to do some algebra. And basically what my goal is I'm trying to get Kc prime, and I'm trying to solve for this equation up here, the original Kc that we had. I'm sorry, I'm confused. What comments are annoying you? I'm trying to understand. Oh, you're talking about for Burleson? Oh, that's for another class. I was like, that has nothing to do with what I'm talking about. And then I realized it is for my other class, so I'll have to answer that later. And once again, it's not showing anything that I'm writing, so I am trying to stay calm. But anyway, I'm going to algebraically solve for our original Kc. Here, maybe you can see my mouse pointing. I'm going to try and solve for this up here, and I'm going to manipulate this so that it becomes that. So yeah, let's see what happens. So first things first, what did I do yesterday? Just squared everything. No, I didn't either. Dang, where's that notebook? Here, I'm back. No, I didn't. It's not going well because nothing's loading. I'm not blaming you.
Look at the key I made.
No, this is what I need. Square everything. Oh, is that what I did? Okay. Well, let's see if this will work again. Please sync. Please do your job. There we go. So now that's what I'm trying to solve for. Let's see if I can do it. So I'm going to square both sides of this is the first thing I want to try and do. Is it going to show that? That'd be nice. I mean, you would think that OneNote would realize and they'd be like, "Oh, he's working on this page. This is the page we need to keep updated." But no, it's not doing that. It's updating who knows what in the background. I'm going to square both sides. After I square both sides, then that gets rid of that 1/2. Okay, so after I square both sides, that gets rid of that 1/2 that I have on B2 right now. And so then what I have is I have Kc prime squared is equal to A2, that looks terrible, A2B squared over A2 squared times B2. And so it gets rid of that 1/2 that I was talking about. There we go. Thank you. And so that's what I ended up doing. And so as you can see, now these two things match. So what that's saying is, oh, well, Kc prime squared is equal to, okay, all this junk, and all that junk over there is equal to Kc. And so if I've done that then, so this is Kc, same thing. So I'm going to have to go in here, tell it to sync again, and hope that it does it. And really, everything's been loaded. What could be causing so many problems? Split in half. I'm afraid I don't follow. So anyway, what I'm trying to show really badly because of my technology issues is Kc prime is just equal to the square root of Kc from before. So it's just algebra. Part 2 is just algebra. So when you end up doing that, you can say, oh, well then Kc prime is going to be equal to square root of 256, which I ended up getting, where did my notes go? 16. And if you're telling me I should have been able to do that in my head, I can't. Golly, this is really annoying. Anyway, there's my work. Now that I've already explained it, and I wrote it minutes ago. So anyway, let's take a look at part C. So for this problem, they've done two things. They have changed the coefficients similarly to what we just saw in part B, but they have also flipped it similarly to what we saw in part A. And so what that means is, just like in Hess's law, if you do one thing, it adjusts it a certain way. If you do both things, it adjusts it both ways. So what we just found is that if you cut all the coefficients in two, you end up having to do a square root of the K equilibrium constant. And if you flip it, you have to invert the equilibrium constant. So for C, we're going to have to do both. So down here, this is going to be flipped and halved. Sorry. Square rooted. Well, they flipped it and halved the coefficients. And so therefore that means we're going to have to invert and we're going to have to square root our 256 value. You need to know your squares according to Miss Bottoms. That must be one of her catchphrases. Okay, so that's what we're going to end up doing. So obviously then our new Kc is going to be equal to the square root of 1 over 256. Okay, and so when I do that, I end up getting 6.25 times 10 to the negative 2. Okay, from my calculator. And hopefully it'll load, because I just wrote this a while ago. Maybe if I start working on the next problem, it'll be ready by the time I actually start talking about it out loud. Wouldn't that be nice? Number 3 is pretty easy. So I guess I can go ahead and write stuff. Seriously, why? Why are you doing that? Now it says it's done, but I've clearly written something. Golly. I need to close things because this isn't doing anything. That's not taking any bandwidth. That's not taking any bandwidth. So anyway, there's the stuff I was just talking about. Let's look at number 3. You guys, I do apologize. There's not a lot I can do about it because I can't seem to figure out why it's not loading in real time, which is what I've been used to. Or else I wouldn't have done this because I've been pretty good with it so far. Let's take a look at number 3. Number 3 is very easy. It says, assuming the system is at equilibrium, select the reaction that goes nearly 100% to completion. The answer here is obviously going to be B. And the reason is B has that Kc value that is much, 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 much greater than 1. And so because of that, we know, oh, I'm definitely still proud to be a Jet, but I am very frustrated with my technology because I really want to help you guys. So if B is much, much greater than 1, that tells us then that your products, okay, are going to be much bigger than your reactants in terms of final concentrations. And so that's how we know. All right, be right back. I'm going to try closing it and opening it again. I don't think it's this issue. Downloads, get updates. Yeah, I don't think it needs to be updated. No, probably not. And see, I don't know what these X's mean. That's the first time I've seen that happen. So anyway, that's what I'm trying to say for number 3. That's what I'm trying to say. And so if products are much bigger, that's why we end up getting that Kc value that's much higher. Okay. Let's take a look at part number 4. The following gas is at equilibrium. At what temperature is Kp equal to Kc? It's at this point that you actually have to start using that equation, which you guys should know. I'll go ahead and write it out right here because we're going to need it. So Kp is equal to Kc times RT to the delta N, and that delta N just is your coefficients of gas products minus coefficients of gas reactants. So it's the sum of your products minus the sum of the coefficients of your reactants. But it's only for gases. We're only really interested with gases here. So Kp equals Kc times RT to the delta N. It's not loading. Okay, so tell you what, since my computer's being stupid, I'm going to mute it for just a second. I'm going to try and just let both OneNotes catch up with themselves. So I'm sorry to do this. Let me just let them take a second. Don't leave. Just take a break real quick. Get yourself something to drink. That's what I'm going to do. And hopefully this will do what it should. Okay, well, I don't know what to tell you guys. Yes, we are taking notes. That's why I was trying to make this short, sweet, and to the point, but instead I write something and it never loads up here. I mean, seriously, I've written something 5 minutes ago, and unless I go in and say sync this notebook, it doesn't load it. So I'm not really sure what the deal is there. And see, now I've just erased it on my computer, on my tablet, and it's not going up there and changing anything. So seriously, I sincerely apologize. I wish there was something I could tell you and I could say, oh, well, this is easy to fix. I know what to do. I don't know what to do. And I've done probably 10 videos now, and I've never had issues like this where I write something and it takes this long for it to show up. See, I've already erased all that stuff, but it's not telling it that, and so it's still sitting on there. Sorry, you can't see it. Here, I'll show you. So see, I'm here. It says test, and I wrote that about 10 minutes ago. I just erased it, and it's not erasing it unless I go in here, right click, tell it to sync notebook, and then it takes it away, which is stupid. I've never had to do that before. So anyway, we'll see what we can do. The correct answer here in number 4 is definitely going to be part D, or answer D. And the reason is with this equation. So the first thing that we can do is we can start off by finding out what delta N should be equal to. Now remember, I just told you delta N is equal to the sum of the gas coefficients of your products. Okay, it's the sum of the gas coefficients of your products minus the sum of the gas coefficients of your reactants. Okay, so you've got to know what that stands for. All right, so gas coefficients of products. I mean, we can, or I can try and work on it now. See, the thing is, if everything were loading, I would already be done by now, and that's why I'm slightly frustrated. Because I wanted to go over the whole thing, because then I could cover the whole class, and then anybody that has any issues with any problem could just watch the video, because that's what I do in my other class. But of course, with you guys, it's not working. I mean, you can, and we can do that instead, and hopefully it'll, load enough that we can struggle through them. So yeah, sure, pick a problem. I'll wait. I am going to finish number 4, though, because I started it. We'll do number 5. Um, so gas coefficients of products is going to be 2 minus 1. So you end up getting 1. So if delta N equals 1, it's basically like that whole term goes away and we don't have to worry about it anymore. Yeah, it's not going to load. Yeah, we'll do those two. So I'll write them down. Well, I don't need to. I can just look in the chat. So we have 5, 14, and 14. So anyway, N goes away. And so then what we're left with in problem number 4, and I know you guys are like, well, I don't need problem number 4. Hold on. Just hold on. Hold your horses. But my thought process is, well then, Kp has to be equal to Kc. And so really we're looking for RT to be equal to 1. We're looking for that product of RT to be equal to 1. And so then you have to think, oh, well, I know that R is always going to be that 0.821 value. Okay, and so if that is equal, always going to stay the same, then you have to find a temperature that you can multiply by that to make it so that product is equal to 1. And so the only one that works here is that 12.19 Kelvin. So when you multiply those two together, you end up getting something close to 1. Good gracious, this is the worst. All right, 5 will be next, and then we'll do 7, and then we'll do 9. And I have to explain 12, apparently. Great. That's fine. And understand, I am not mad at you all. I'm very frustrated with technology right now because I should not be having these issues. And yet here I am. Anyway, when you end up doing that, RT goes to 1, and so that just makes that term go away, and then Kp is equal to Kc. All right, let's look at number 5. So select the reaction for that equilibrium constant. This is just algebra, guys. You can take the time to go through number 5 and just look at each of them individually and say, oh, well, how could I rearrange this? Well, how could I rearrange this to make this work? First things first, you need to start by writing your Kc. Well, like rearranging it, because that's kind of a stupid way to write it. You can see they've put Kc over on the right side, and they've put one of the concentrations over on the left side, and that's just dumb. So I'm going to rearrange it so that instead I have everything the way it should be. So basically I'm dividing Kc on that side. Or sorry, I'm going to leave Kc where it is. I'm going to divide over AB2 squared and B2. And so by doing that, I get this. AB3 squared over AB2 squared times B to the 2. So basically all I've done, hopefully it'll pop it up. Wow. It'll pop up part of it so that I'll just be annoyed. I'm going to drink some more tea. Not enough sugar. There we go. So now all I've done, as you can see, I've rearranged Kc so that now I have everything the way it should look, the way that you're used to seeing these equilibrium expressions written. And so now we can say, oh, well, then my product is going to be AB3, and that exponent up above tells me it's going to have a coefficient of 2. Okay. And then I can say, oh, well, then my reactants, here's my reactants down here in the bottom. So I'm going to have reactants of AB2 and B2. And AB2 is going to have a coefficient of 2, and B2 is going to have a coefficient of 1. Okay, so literally I'm just saying, all right, well, here's what we know based on those things. Please load. There we go. And so then you can kind of piece together the reaction that they're talking about. So then I can say, all right, well, AB2 is going to have a 2 plus B2 yields, well, double arrow, 2 times AB3. And so then you can look at your answer choices and you can see that answer choice C is the only one that's correct. So it's basically, problem number 5 requires you to understand, okay, what does that equilibrium expression actually mean? How can I get a chemical formula out of it? And again, I have written the answer. It's just not showing the answer. There you go. And so that's why. That's why. All right, next one I see is question number 7. So we'll go take a look at that real quick. And guys, if my explanations are not sufficient, please ask follow-up questions. Okay, it's not like regular class. You need to actually ask me follow-up questions. All right, so you have to type them. All right, let's look at number 7. Let's look at number 7. Oh, yes, this one. Excuse me. I feel like I have a sneeze coming, but I'm not sure. Yeah. Excuse me. That was excessive. So in problem number 7, if you can really, you can do no math. You can do no math, and you can get the answer to number 7 just by looking. Okay, cool. Do that. That is, So that tells me it's just my computer. That's interesting. I will look into that later. Okay, so anyway, let's take a look at number 7. It says, consider the following reactions in equilibrium concentration. And every species, that means everything, reactants and products, is going to have a concentration of 0.01 molar. And so, yeah, you have the means to go through and do the math to find out every single one of these. And you could just say, oh, well, I can write a Kc expression for all of these. Then I put in 0.01 as every concentration, and you can do the math. Yeah, guys, if you want to try what Emily's talking about, that's fine. If it's loading fast on your computer, do that. And I will talk you through it, and I'm going to be writing on mine. If you're wondering where we're working, I'm in my Unit 7 folder, and I've just called it Unit 7A Problem Practice. Okay, so you can see right here on my screen right now. And I don't know, I'm not sure why my OneNote is being stupid, but it gives me hope that it's working on y'all's, so that's great. So anyway, let's take a look at number 7. So you can do that, but when I look at problem number 7, I start by just saying, okay, the extent of reactions taking place. So basically what they mean then is which one is going to go the most towards products. We're really we're really looking for which one is going to go the most towards products. And so if you think about a Kc reaction, we're just looking for something that has a really large, numerator, and yeah, a relatively small denominator. So we're looking for something like that. And so if you look at it that way, you can say, oh, well, based on what I'm seeing, reactants are pretty high in problem number 3, Is that what I meant to say? I don't think that is what I meant to say. Here, I'm going to just write them out because that'll make more sense than me trying to explain it verbally. So if we look at the Kc for each, I'm not even going to plug in any numbers because we know that all the concentrations are going to end up being 0.01. So I'm just going to show you. It's products of reactants. So over this one we have PCl3 to the 1 times Cl2. That looks terrible. To the 1, and this is all going to be over PCl5. And so the ratio that we're looking at here is basically 2/1. Think of it like that. This is a 2/1 type ratio for number 1, because you have 0.01 times 0.01 all over 1 down the bottom. Nope, I don't like that because it's 0.01. It's going to end up being smaller. But anyway, next one we want to look at is problem number 2. And so if we look at that one, we can say, all right, well then Kc is going to be equal to products of reactants again, H2 times I2, and this is all going to be over Hi squared. And so this one right here basically just ends up being equal to 1. If you think about the Kc value here, it's just going to end up being equal to 1 because you have 0.01 times 0.01 on the numerator, and then you have 0.01 squared on the bottom, which is the same thing. So this whole 1 is going to end up equaling 1. The next one that we're looking at, problem number 3, I'm going to move it over here. All right. You can look at that one in the same way and say, all right, well, products of reactants, so we're still going to have ammonia on top, and this is going to be squared, and this is going to be over N2 to the 1 times H2 to the 3. All right, so we end up getting that. And so when you think about this in terms of 0.01, if you do 0.01 times 0.01, where's my calculator? There we go. Nope, that's not what I wanted to type. There we go. So the number actually ends up getting smaller. And so what you'd see then is 1 is going to be the smallest. If you think about it mathematically, 1 is going to end up being the smallest because what we have is if you have 0.01 times 0.01, that's going to end up being a very small numerator. And so this Kc value is going to end up being less than 1. Then we look over at this Kc value for problem number 3, and we'll see, okay, this is 0.01 times 0.01 because it's squared. But down here on the bottom, it's basically 0.01 times itself 4 times. And so what that tells us is that that's going to have a very large numerator, a very small denominator, and so this Kc is going to be much greater than 1. So even though I'm not really typing anything into the calculator, you can kind of look at these and understand, at least in a way, what's going to end up happening and what this stuff actually means. And so remember, if Kc is equal to 1, that means that it's kind of an equal mix of concentrations of products and reactants at equilibrium. If you have a Kc value that's much less than 1, that means it's tending towards reactants, and it's not a very forward progressing reaction. It stays towards the reactant side. It doesn't go towards products. And then if you have a Kc value that's much greater than 1, that means that it does go really, really, really far to the right. And so based on all that information then, we can see that 1 is definitely going to be the smallest. We can see that equation 2 is going to be right in the middle. And we can see equation 3 is definitely going to be the largest. And so that is why answer choice B is what we're looking for here. That's why answer choice B is the answer. All right. I'm trying to get it to load, and, well, you know how that goes. All right, so we did 7. Apparently now I need to talk about 8. And again, guys, if I'm not being clear enough, please, you guys are fast typers. Just type something in there. There's about a 25-second delay with YouTube. That I'm used to. It's the OneNote problem I'm not used to. So if you do have a question, please type it. And if I need to go back and answer it, I'll answer it. Let's take a look at problem number 8. Consider the equilibrium at 295 Kelvin. They give us a reaction here. And it's also giving us the partial pressure. So calculate Kp, calculate Kc for this reaction. All right, so here's the deal. For this problem, you are going to be looking for Kp and Kc. And obviously, they give you a lot more information for Kp. They're giving you much more information for Kp than Kc because they're giving you partial pressures. Okay, they're giving you partial pressures. And so the first step that we're going to want to do is solve for Kp. So let's do that. All right, let's solve for Kp. So Kp is going to be equal to the partial pressure of NH3 times the partial pressure of H2S. Now remember, even when you're doing Kp, it's still going to be products over reactants. Neither of these, it is balanced, right? Yeah. Neither of these have coefficients, so there's no exponents involved. It's just product times product. And we're going to have no reactants in our Kp because, as you can see, that is a solid, and so we're not going to have it. All right. So Kp equals pressure, partial pressure of ammonia times the partial pressure of this dihydrogen sulfide. All right. And so when we do that, we use the numbers they gave us. They're both going to end up being 0.265 atmospheres. Okay. And so we do some math. Boom, 7.02 times 10 to the negative 2. And that is one of our answers right there. They're giving they gave us Kp. You just had to do a little bit of math to figure out what it is. Okay. And of course, it's loading part of what I've written. Anyway. So the next thing that we have to do is we have to find Kc, and this is where that equation comes in handy. So I'm going to go ahead and write out the equation. Kp is equal to Kc times RT to the delta N. Delta N in this case, because it's the sum of the gas coefficients of products minus the sum of the gas coefficients of reactants. And so we just have 2 minus 0. So delta N is going to end up being 2. Okay, it's going to end up being 2. R is a constant. T is 295, so we could even do the math to find that out. In fact, I think that's what I'm going to do. I'm going to rewrite. Kp, we know, 7.02 times 10 to the negative second. Kc is what we're solving for. RT is just going to be 0.0821 times my temperature, which is 295. And so I get 24, but wait, that's squared. And then I get 586. So it's going to be Kc times, really big times, 586.6. I don't know. It has some units. I'm not real worried about the units right now because I know that my final answer is going to be unitless because K values never have units. So 7.02 is equal to that times that. I'm going to end up dividing 586.6 Okay, and I'm obviously divide it the same thing over here. So we end up getting a Kc value equal to 1.20 times 10 to the negative fourth. So this one's just kind of a math problem, honestly. It's just understanding, look, they gave you a lot of stuff about partial pressure, but they gave you just enough so that you could solve for your Kc value. Okay. All right, looks like the next thing we're going to talk about is problem number 9. Problem number 9. All right. So one of the things that my wife told me that I do think is worth mentioning for problem number 9 is that this problem gives you a piece of information, but they don't put it in the right place. So they tell you delta H is equal to 38.5 kilojoules, and that positive value tells us that the reaction is endothermic. Remember, delta H is always based on the system. So if you see a positive 38.5 kilojoules, that is telling you and saying, oh, well, this reaction is absorbing energy, it's taking in energy. And so whenever you're doing Le Chatelier type problems, which that's what this is Le Chatelier problem where you're going to say, which way is it going to shift? Why is it going to shift that way? But heat, it is more helpful to put in the chemical equation rather than leaving it right there as delta H. So all I'm going to do is, because it's endothermic, heat is going to be in the reactants side. So I am actually going to rewrite it right over on the left. Excuse me. Excuse me. Well, I did write it. Seconds ago I wrote it, but it's not going to load. Okay. Anyway, put heat on the reactant side. So even though they don't do it, it's helpful to do it for you because we're going to need it here in a second. Number 1. The reaction mixture is heated at constant volume. So right away, this is why it's helpful to have heat written over there. Because if it's heated at constant volume, basically think about it like, instead of increasing the concentration of one of the reactants, one of the products, now what we're saying is, no. You're heating it, so you're increasing the heat. So it's like you're increasing the concentration of one of the reactants, which in this case is heat. And so if you increase concentration of reactants, you have more reactants. It's more likely to cause collisions, so that it's going to send to the right. It's going to send towards the product side. So whenever you're doing Le Chatelier, it's helpful to think about it in terms of, okay, you can think about it like a seesaw. For me, I don't know, I guess I'm weird. I like to think about it like, imagine 2 beakers. Okay, imagine 2 beakers. And one beaker's here, one beaker's here, but they're connected with a tube at the bottom. Okay, they're connected with a tube at the bottom. So if you add more liquid to this side over here, maybe right now they're balanced, but if you add more liquid to that side over there, isn't liquid going to push down and travel through the tube over to the other side to bring everything back to balance? Yes, it will. And so typically when I think about concentration questions or I think about heat questions, that's how I think about it. I say, oh, well, if it is heated, it's going to increase, that reactant, which we know heat's not really a reactant, but we're treating it like one. So if you increase the heat, it's going to want to get that concentration balance back again. Now remember, that doesn't mean concentrations are equal. It doesn't mean that your reactants and your products are going to be exactly the same. But if you increase the heat, it's going to want to form more products to bring everything back to that equilibrium. It's going to want to take away reactants and form more products to get that concentration balance to what it should be at equilibrium. And again, that does not mean equal. In equilibrium, the only thing that's equal is the rate that is occurring. So it's how much is being formed. Anyway, so if the reaction mixture is heated at constant volume, you are going to shift to the right. Okay, so you're going to shift to the right, and you can say, because reaction is endothermic. Okay, that's the deal. That's the reason. Next one, number 2. It says NF2 gas is removed from the reacting mixture at constant temperature and constant volume. So that's important. So nothing else funny is going on. Literally, magically, I imagine, they extract this nitrogen difluoride from this, I don't know, flask, who knows, reaction chamber. So again, I think about it in terms of those levels. And I say, all right, well, we start with everything equal. But if you start to remove one of the products, well, then the reactants are going to have to form. They're going to start to form because now there's more reactants than there should be in terms of a ratio at equilibrium. And so, again, look at it this way. Start with balanced. But if you remove that product, then the reactants are going to react to form more of that product. Okay, and these go down, these go up until everything comes back to equilibrium. But again, it's still going to shift to the right. It's shifting to the right because it has to reform some of that product that was removed. Okay, so it's going to shift to the right to counteract a decrease in product. Okay. Number 3, the pressure on the reacting mixture is decreased at constant temperature. Whenever you're dealing with pressure, whenever you're dealing with volume, I kind of go through a mental, logic, line of logic to try and explain it to myself. So if pressure is decreased, right? If pressure is decreased, that means there's less pressure pushing the gases together. Okay, there's less pressure pushing the gases together. So if there's less pressure, that means there's more room for the gases to move around. And so if you decrease pressure, you give the gases more room to move, the reaction will shift to the side of the reaction with more moles of gas. So let me write down that line of thought again. Let me actually write it down. So less pressure means more room for gas. More room for gas means it will shift towards side with more moles of gas. And so when we look at this reaction then, we can see that one side has 1 mole of gas, that dinitrogen fluoride thing, tetrafluoride, excuse me, over on the left side. And on the right side, we have 2 moles of a gas, of that nitrogen difluoride. And so obviously then, the side of the reaction that has more moles of gas is going to be to the right. So again, still going to shift towards the right. In fact, I'll write it over here. Right. Number 4, an inert gas is added to the reacting mixture at constant volume and temperature. Inert. So inert gases, by definition, mean that they are not going to react with anything. Okay, so you might be thinking, oh, well then if you add an inert gas, it's not going to do anything. Yes, it will, because it is still a gas. So if you add more gas to this reacting chamber, this reacting mixture, then really what you're doing is you're increasing the pressure. So if you, even though it's inert, even though it's not going to react with anything, maybe it's, I don't know, maybe it's argon. Throw some argon in the mix and see what happens. It's not going to react with anything. But if you add argon in there, what is going to happen is it's going to increase the pressure inside the chamber. So it's going to be the opposite of everything I just said in problem number 3. So more gas means more pressure. Okay, more pressure means less room for gas. Less gas room means it will shift towards side with less moles of gas. Okay, and so the side with less moles of gas in this case is going to be the left side. So that's going to be my answer. All right, it's going to be the left side. All right then. So we did number 9. Looks like we're going to do number 12. We're going to talk about number 12. Let's take a look at it. You guys are good on number 10? I'm shocked. But all right, we'll look at number 12. In which of the following reactions the equilibrium remains unaffected on the addition of a small amount of argon gas at constant volume? Excuse me. All right, and I do apologize. I know you guys hate the handkerchief, but I love the handkerchief. And now, handkerchiefs are super popular everywhere. I went to Lowe's. Everybody's wearing their handkerchiefs on their face now, so they're really proud of their handkerchiefs. So anyway, problem number 12. So in which is the equilibrium going to stay the same, and it has to do with the small amount of argon gas at constant volume. This is based on what I just said. Oh, okay. Well, Kat, I will go back and do number 10 then. I will go back. Hold on. So this is based on what we were just talking about with number 3 and number 4 in that last problem. Okay, you've got to think about it as saying, oh, well, if you add an inert gas, okay, yeah, it's not going to do any reacting. It's not a reactant or a product, but it is going to increase the pressure. So if you increase the pressure, what is that going to do? It's going to shift towards the side with less moles of gas. And so all we're doing in problem number 12 then is we're looking at these different situations and we're saying, oh, well, which side has less moles of gas? Well, let's take a look at A. So in A, we have 4 moles of gas on the left. We have 2 moles of gas on the right. So if I add more argon, yeah, it's going to shift. In fact, it's going to shift to the right because that's the side with less moles of gas. Remember, if you add an inert gas, that's more pressure. More pressure is pushing the gases closer together. So it's always going to shift to the side that has less moles of gas because there's not as much room for that gas now. So in problem number A, or sorry, letter A, it's going to shift towards the side with less moles of gas. B, we got 1 mole of gas on the left. We got 2 moles of gas on the right. Same thing. There is a difference in the number of moles of gas, and so it's going to shift towards the side with less moles of gas, and this side towards the reactants side. But then in problem C, H2 gas, iodine gas, has 2 moles on the left, 2 moles of hydrogen iodide gas on the right, 2 moles, 2 moles. So if you add additional argon gas, the concentration is going to stay the same. The equilibrium is not going to shift because there's not one side that has more moles of gas. Okay, so our answer number 12 is going to be C. All right, it's going to be C. All right, let us continue. Let's look at number 10. So number 10. All right, guys, I'm going to teach you a fantastic method that I learned at the Summer Institute, but because they were going so darn quickly, I had no idea what in the world they were talking about. But now I do, because my lovely wife helped explain it a little more slowly. So this is an ice table problem, okay? Ice. I do not have ice anywhere. I don't usually drink ice in my drinks because it waters it down. But ice is extremely helpful when you're dealing with a problem like number 10, and coincidentally, also like number 14. So get hyped for that one. We'll look at that one in a moment. But what ice stands for, and I am gonna have to force this to load because I need it. What ice stands for is initial, change, and equilibrium. And so an ice table is just a way of organizing your thoughts to try and understand what's actually going on. So in problem number 10, I'm actually going to write it right underneath that chemical equation. That's the way you should always do it. So if they don't give you a chemical equation, write it, okay? Balance it, and then write your ice table right beneath it. And so that's what I'm going to do here. So I, C, E. So initial. In this problem, it says a sample of potassium pentachloride gas, excuse me, is introduced in an evacuated vessel at 450 Kelvin. After equilibrium was attained, the concentration of PCl5 was found to be 0.05 molar. If Kc is 0.0083, then calculate the concentrations of PCl3 and Cl2 at equilibrium. So we've got to have this ice table. So here's what you got to think of. Do we know the initial concentration of our sole reactant, PCl5? So look at the problem. No, I know nothing about the initial concentration of PCl5. What I do know is the equilibrium concentration of PCl5. So now I can actually start writing in my table. And I'll try and explain it actually after it actually writes. I also know the initial concentrations of PCl3 and Cl2 because before anything has happened, okay, it says it was an evacuated vessel. So that means it was a completely empty container. So if you start with a certain amount of PCl5 and then you're going to start with 0 of both of your products. So we're going to start with an initial concentration of 0 for both of those. All right, let me refresh. Try to, since this thing's being so stupid. There we go. Now, I put that little dash there under PCl5 because honestly, we could give a crap. All right, we don't care what the initial concentration is. That's not going to help us any. But what is important is to understand that PCl3, Cl2 both start with an initial concentration of 0. Another thing that we know that we can go ahead and put in our table is that at equilibrium, my final concentration of PCl5 is going to be 0.05 molar. So I can go ahead and put that in my table as well. The change, yeah, we're going to need to know that in a second. I need to know that. Or do I? No, because I only need to know equilibrium. So here's what we got then. Let's sync it again so you guys can see what I'm looking at, hopefully. So what we're looking at then is we start with 0 and 0 for both of our products. We know that we end with a concentration of PCl5 at the very end. But now we got to talk about the change. Now, this reaction has already been balanced. So we can see we have 5 moles of chlorine over on the left side. We have 5 moles of chlorine over on the right. We got 1 mole of phosphorus over on the left. We have 1 mole of phosphorus over on the right. So it's already been pre-balanced. And so what that means then is for every 1 mole of PCl5 that you lose, you gain 1 mole of PCl3, 1 mole of Cl2. Now, we're not dealing with moles per se. We're dealing with concentration. So we're dealing with molarity, moles per liter, and all that junk. But what I'm actually going to do is I'm just going to write it this way. Let's treat it like a math problem. If I increase my concentration of both of my products by X, okay, just good old X, the thing you're always looking for in math class, then I'm going to decrease my single reactant by negative X. So as you increase PCl3 and Cl2 by X, you're going to decrease PCl5 by negative X. Why is my table not uploading? Please, OneNote, do your job. Thank you. And so now I've updated this table to make a little more sense. So what that means then is at equilibrium, this ubiquitous X, that's going to be my amount of PCl3. That's going to be my amount of Cl2. So to finish out the ice table then, we know that at equilibrium, this is what we're going to end up having. 0.05 molar of PCl5, and we're going to have X molar PCl3, X molar Cl2. Please. Okay, take a second, make sure you understand what I'm talking about and you understand what these numbers mean. Because the next part of the problem, it's not super hard, but I do need you to make sure you understand where this ice table came from. I didn't just make it up. There you go. Now it's filled out. It's a very important table. Do the 2 or 3 of you that are still here actually get it? Oh, there's 5 of you still. Wow, thank you. Thank you for staying with me. All right. So if you understand that, now you've got to think about this. The only part of the ice table that really matters now, because it helped us organize our thoughts, which was great. But the only thing that we really need is that last row. Okay, we only need the equilibrium part, because remember, the problem gave us a very useful number. Not only did they give us 0.05, but they also told us that the Kc value was 0.0083. So think about what that gives us. We can now write a Kc expression for this thing, and then say, all right, well, Kc, products over reactants. You guys know, how it works. So I'll say, all right, well, PCl3 times Cl2 all over PCl5. Okay, so there's my equilibrium expression. Hopefully it'll load this time. Nope, it didn't. Of course not. But now we're actually going to plug some numbers in. Because we know Kc is actually 0.0083. we know that PCl3 is actually going to be X, okay, at equilibrium. We know that the concentration of Cl2 is going to be X at equilibrium. And then finally, we know the concentration of PCl5 is going to be 0.05 molar. And so now, when we write it that way, try and sync again. Now, we have something we can calculate because we're looking for those final concentrations. So again, all I did, I organized my thought process using this ICE table. I said, all right, let's think about it this way. We have initial concentration. We find out what the change is. And because it's 1 to 1 to 1, there are no coefficients anywhere in this chemical reaction because it's 1 to 1 to 1. We're able to say, oh, well, if PCl5 goes down by X, PCl3 goes up by X, Cl2 goes up by X. That's our thinking here. But then at equilibrium, we know how to write an equilibrium expression. That's super easy. But instead of plugging in concentrations for that phosphorus trichloride or the chlorine gas, we're just going to plug in X and X. So we end up getting X squared. So what we have then is just a, I don't know, fairly simple algebra situation where we say, oh, well, 0.0083, okay, times 0.05, because we got to get it out of the denominator. And then we'll square root it, because we have X squared on the top, so we'll square root that answer, and then we end up getting X is equal to a number. There it is, 0.02 molar. So math happens. X equals 0.02 molar for both. All right, let me load this. Hopefully it'll show all that work I just did, sort of. All right, well, guys, please comment. If you get it, great. If you don't, please tell me. Okay, make sure you understand what I just did, because the next problem's a little bit harder. So I need you to make sure you get it. 12. Did I explain 12? Yeah. So all we got left to do is 14, and 14 is just a harder version of number 10. That's why I'm glad we went over number 10 first. There we go. Now it's showing. Thanks a lot, OneNote. No questions? You guys get it? You understand how an ICE table works? All right, I'm going to take your silence as yes, that makes perfect sense, Mr. Nairn. This was super easy. Let's look at number 14 because it's not easy. It's going to be a very similar situation. We're still going to use an ICE table. We're still going to use an equilibrium expression to try and do math to figure out what everything means. But this one's a little more confusing. Okay, so it says 1 mole of each of A and B and 3 moles each of C and D are all placed in a 1 liter flask. The equilibrium constant is 2.25. All right, so that's helpful. So we know the equilibrium constant. So once again, we're going to be heading towards writing an equilibrium expression at some point. Okay, we are going to do that. But what's more important right now, for 14, is that we actually write down that ICE table. So I'm going to rewrite the chemical formula so it's a little more accessible. A plus B is in equilibrium with C plus D. And then I'm going to write out my ICE table. I means initial, C means change, and E means equilibrium. Okay, let me see if it'll show that. That'd be really nice if it would. Or at least part of it. You know, just show me part of it. Load half of it, just enough to annoy me. Okay, or not, or load nothing. That's fine. So it gives us some initial concentrations of all of this stuff, which is really useful. Okay, we know that initially A is going to be 1 mole. I wrote an I. It's going to be 1 mole. And by the way, because it's in a 1 liter flask, I'm sorry, Kira, I doubt it has been super helpful, but have a good day. Even though it says we start with 1 mole each, because it's in a 1 liter flask, 1 mole per liter is just going to immediately turn it into 1 molar. So we'll have 1 molar of A, we'll have 1 molar of B, we're going to have 3 molar of C, we're going to have 3 molar of D. All right, let's try and load this again. Because I've actually written some stuff. OneNote, thank you. So see, we know all this initial stuff. That's pretty helpful. But now we've got to think about it in terms of change. Now, in this problem, they have no coefficients anywhere. And so what we're forced to assume is that they have a 1, a 1, a 1, and a 1. They all have a coefficient of 1 written in front of them. So what that means then is that for every 1 mole of A that is consumed, 1 mole of B is also consumed, 1 mole of C is produced, and 1 mole of D is produced. So again, it's a 1 to 1 to 1 to 1 thing, just like we had in the previous problem. Okay? So it's just like in the previous problem. So what I'm going to say then is I'm going to say, all right, well, A is going to change by negative x. Okay, B is going to change by negative x. C is going to change by positive x. And D is going to change by positive x plus x. All right, let's sync so you guys can see what I see. Maybe. Or not. Or not. Sync this notebook, please. Okay, well, we're going to keep on going anyway because we have to. And so now we have to think about it, say, well, if the change is just negative x, for A, for instance, then we can say, oh, well, if it was initially 1 molar, it'll just be 1 minus x at equilibrium. And oh, for B, same thing. If it was 1 molar initially and it changed by minus x, then B is just going to be 1 minus x at equilibrium. And I think you see where this is going. When you get over here to C started with 3 molar and it's going to change by plus x, so it's going to be 3 plus x at equilibrium and 3 plus x at equilibrium for D as well. Okay, so this is what we end up getting, maybe. All right. And so now we have to do a little bit of math. Okay, and honestly, if you can just get the ICE table done, the rest of it is just algebra. And I know this is not an algebra class, but you got to know this math. You've got to be able to understand how they're doing this math. So let's see what happens at equilibrium. So remember, we are going to write our equilibrium statement, that equilibrium expression. Kc is well, it could be Kc, yeah, because we're dealing with concentration. So yeah, it's going to be Kc. Products over reactants, we have C times D over A times B, products over reactants. But at equilibrium, please do your thing. Wait, don't close the notebook. Dang it, I hit the wrong button again. I hit the wrong button. This is a disaster. I just closed the whole notebook. But I did it yesterday too, while I was also freaking out and trying to get things to work. So, you know, what are you going to do? Let's go here. Let's go here. Come on, OneNote. Don't do this to me. There we go. Let's see what it shows. Yay, it has everything written. So we're still okay. We're still okay. So here's what I've got written so far. As you can see, I have my Kc expression. I already have my ICE table fully completed. And again, ICE table is just a way of organizing your thoughts. It's just a way of trying to spell everything out so that now, for the next step, we're going to plug all this stuff in. So this 1 minus x, 1 minus x, 3 plus x, 3 plus x, we're going to plug those in for the concentrations in the Kc expression. So we end up getting this abomination. Give me a second. I'm writing it all out, and then I'm going to try and load it again so you guys can see it. Okay. All right, so now we have this. Okay, so see, algebra. I just plugged in the values where they should go into this Kc expression. But now what we're going to do is we've got to do the algebra. We are looking for x here. We know what Kc is equal to. In fact, I'll write that down. Kc is equal to 2.25. Okay, so now it's just algebra. I'm going to just scroll down and focus on the algebra for a little bit. So we can say, all right, well, 2.25 then is equal to 3 plus x squared over 1 minus x squared. Just trying to simplify it so that the math will make a little more sense. Just trying to simplify it so the math makes more sense. We'll see if OneNote does that or not. There we go. So now it's just algebra, guys. We're looking for x. Find x. So I think the first thing we're going to do is we're going to square root everything, because if we square root everything, we can get rid of those squares that are so annoying. So I'm going to say, all right, well, square root of this, square root of this, gets rid of those squares. Square root of 2.25 gives me, is it 1.5? No. What in the world? There we go, 1.5. So 1.5 is equal to 3 plus x over 1 minus x. So that's our new statement. Okay. Well, it's thinking about it. Again, we're just doing the algebra. And then we will then explain what the math means here in a minute. But for now, we're using the math as a very helpful tool. Okay, so now that I've done this, I'm going to go ahead and clear out the denominator first, because I don't like fractions, and you shouldn't either. Makes algebra a lot more difficult. So by getting rid of that 1 minus x on the bottom, I'm just going to multiply by 1 minus x on the one side. I'm going to multiply the other side by the same thing. That cancels it. And so then what we end up getting is 1.5 minus 1.5x is equal to 3 plus x over on the right. Maybe. There we go. So this is what we're looking at now. That's the step of the math that we're in. So next thing we're going to do is we'll just add the 1.5x over to the other side, because we can. So plus 1.5x on the left, plus 1.5x on the right. And by doing that, now we have 1.5 is equal to 3 plus 2.5x. And then obviously we want to get rid of that 3 as well. So we're going to subtract 3. We're going to subtract 3. And so, long story short, after you've done some math, okay, let me show you what that looks like so you guys can see where I am. Maybe. There we go. And so now what I have is I have negative 1.5 is equal to 2.5x. So obviously you'll divide both sides by 2.5. And long story short, we end up getting x is equal to negative 0.6. And you may not like that. And you might say, well, how can you have a change of negative? You can. Of course you can. In this problem, we were not starting with 0 and 0 for products. They were starting with 3 molar and 3 molar. And even if you're dealing with a reaction that has a positive, greater than 1 value, Kc value, that tells us it does tend towards products, but it doesn't necessarily, it means it needs to go all the way to 3 molar for each of them. And so now that we know that our x value is 0.6, now we can actually find out what our equilibrium concentrations of A and C are respectively. And I gotta be honest, my wife and I both talked about it, and it just sounds dumb. It says calculate the whole problem says calculate the ratio of the equilibrium concentrations of A and C respectively. Not really sure what in the world they're talking about there, but what we can do is find out what the equilibrium concentrations will be and just kind of go from there. So for A, 1 minus x, remember, 1 minus x we determined to be, it doesn't show, but x we determined to be negative 0.6, Okay, so x is negative 0.6. So when we come up here, we can say, all right, well, 1 minus x, that means this is going to become positive 1.6 molar at equilibrium. And for C, 3 plus negative 0.6 means I'm going to do 2.4 molar at equilibrium. Okay, and so if you really wanted to do a ratio, I mean, technically it's a 2 to 3 ratio of A to C, but I don't really know what this problem's looking for. I don't know what they mean, ratio of equilibrium concentrations, respectively. Don't know. I don't know what that means. Okay, I don't know if that means compared to what its initial concentration is. Heck if I know. But what I do know is you can solve for it this way. If you want to say this is a 2 to 3 ratio, you can. But, I mean, that's really not what we're looking for. It's more important to me that you guys can find what these equilibrium values are, and you can explain whatever it is they're looking for. Okay. All right, guys, we struggled through this. I'm going to be calling tech support here in a minute because this should not be working this slowly. And so I'm going to see if they can tell me anything. I am very, very, very sorry for the technical glitches. I wish I knew what was going on because I have not had this issue until yesterday. And then all of a sudden yesterday, this has been my life. So I don't know. I'm going to call tech support, see if they can help me a little bit. Do you guys have any other questions before we get off the stream? Do you have anything else before I get off? And I do know there is a 25-second delay for you guys to answer, so if you don't say anything after 25 seconds, I'll just leave. Seems to be what's going on anyway. You guys do have a little bit of notes to take today. I'm sorry to burst your bubble. It's in the instructions. I made it very short. So I picked you the shortest section we probably had so far, which is section 17.3. You guys have a great day. If you need anything, please send me a remind message, send me an email, whatever you need to do. And maybe next time we try and do this, it won't suck so bad. Have a great one, guys. Be proud to be a Jet. See you when I see you.